Okay, so this is going to be our lesson on the derivative and integral of y equals e to the x. All right, so what we're going to do first, all right, is discuss a property of natural log and e to the x and their inverse relationship, because we're going to use that to develop the derivative of y equals e to the x. But then we're also going to use that to solve a particular type of derivative, all right, as we go through our lesson today. So now, y equals natural log of x and y equals e to the x are both inverse functions. All right, so because of this, we can solve natural log problems by exponentiating, and we can also solve exponential problems by taking the natural log of both sides of an equation. We can also use this fact to rewrite things in equivalent forms. All right, and that's what we will do, all right, to help us with some of our work today. All right, so let's look at the derivative of e to the x. Okay, so what I'm going to do, all right, to develop the derivative of y equals e to the x is take the natural log of both sides. All right, so we worked on this last week, so in the natural log of e to the x. Okay, so now one of the properties we discussed last week is that if the argument is raised to a power, we can move that power out front. So that would be x natural log of e. Now, when I look at what we have now, okay, the natural log of e is 1, which is going to leave us x. All right, so now I'm going to actually take the derivative. All right, so the derivative of the left side. So we talked about this. The derivative of natural log of u is 1 over u. So in this case, that's going to be 1 over y. And then times du dx. And the derivative of y would be y prime. The derivative of the right side, the derivative of x, is just 1. And so to solve, all right, for y prime, we're going to multiply by y. So y prime would equal to y, which means that y prime, if we go back to our original relationship, y was defined as e to the x. So the derivative of e to the x is simply e to the x. All right, so a very easy one to remember. So if you need to see that in writing, here's a little bit more. So that's the same process I went through in a little bit more detail should you need to see that again. All right, and remember also, we have to chain rule it. All right, so remember if we have e to the u, all right, it's going to be the derivative of e to the u is e to the u, and then we have to do the du dx part as well. All right, so let's actually look at some examples here. All right, so we want to take the derivative of, all right, e to the 2x minus 1. So the derivative of e to the u is e to the u, so that's going to be e to the 2x minus 1. And then I'm going to multiply by the derivative of our u, so in this case it's 2. All right, and if you want to, all right, you can just put that 2 in front, so 2 times e to the 2x minus 1. All right, so what I'd like you to do now is go ahead and attempt the second one. So go ahead and pause the video, all right, try to do this yourself, and then turn the video back on, and you can see me work through the problem. Okay, so hopefully you have this problem complete. So the derivative of e to the u, all right, is e to the u, so e to the negative 3 over x. And then I have to multiply by the derivative of this piece. So this is really a power rule problem, right? So this is really negative 3 times x to the negative 1, all right? So this is really what our u is. So then if I apply the power rule, all right, I'm going to multiply by negative 1, so that's going to become a positive 3, reduce it, all right, by 1 power, so that. Okay. Now, if you clean this up, the 3 and the e to the negative 3 over x will be in the numerator, so it would be like this. And this x to the negative 2 is, all right, going to go to the denominator like that. All right, so that's how we take the derivative of e to the u. All right, so now let's look at this in combination with another type of problem that we've looked at this year. All right, so now these things that we've learned, like natural log of x and e to the x, can be worked into, all right, some of the other problems that we have discussed this year. So notice if we take the derivative of g here, all right, so let's say g prime of t, okay, that we're going to follow our rules that we have established so far this year. So our main rule so far is power rule. So I'm going to take the 3 out front. I'm going to take and reduce, all right, this by 1 power, so that's squared. And then we have to chain rule it. So now I have to multiply by the derivative of the internal pieces. So the derivative of e to the negative t will be e to the negative t, and then times the derivative of negative t, which is negative 1, plus the derivative of e to the t, which is just e to the t. All right, and so then that's my derivative, and that's all the work you need to do. All right, so let me go ahead and move to the next example. So once again, what I'd like you to do is just go ahead and pause this video, all right, and do this on your own, and then I'll work through this with you in just 1 second. All right, let's see how you did. All right, so let's take the derivative. All right, so notice here that our main rule is the natural log function. All right, so y prime equals. And the derivative of our natural log of u is 1 over u. And our u this time is 1 plus e to the 2x. All right, and then we have to take the derivative of this. Derivative of 1 is 0, and then derivative of e to the 2x is going to be e to the 2x. And then times our exponent, derivative of our exponent, which would be 2. And so that is your derivative. All right, so let's just kind of keep moving on with some of our example problems here. All right, so one more. All right, so go ahead and attempt this one on your own. So pause the video, work through the problem, and then you can turn the video back on and see how you did. Okay, so I'm going to work through this now with you. All right, so you can see your work. All right, so the derivative of natural log of u is 1 over u. All right, so the 1 over u part really is just going to give us the reciprocal of this. So that's going to be 1 minus e to the x over 1 plus e to the x. All right, then I have to take the derivative of this guy, which is going to give us a quotient rule. All right, so our quotient rule is the derivative of the numerator. All right, so the derivative of our numerator is going to be just e to the x times our denominator minus, maybe I need to go ahead and get this parenthesis out of the way here. All right, minus our numerator, which is 1 plus e to the x, times the derivative of our denominator. And so the derivative of our denominator is going to be just minus e to the x. And then that's all over, all right, our denominator squared. All right, so now if you clean this up a little bit, all right, you can see some simplification things you can do that are pretty simple. So this 1 minus e to the x here will cancel with one of those there. All right, so now in our denominator, we only have 2 expressions, so 1 plus e to the x, and then we only have the 1 minus e to the x here. And if you look up here, I think if we distribute some of these, we might get some things that cancel out. So e to the x times 1 is e to the x, and that's going to be minus e to the 2x. So remember, when I distribute two things or multiply two things with the same base, I add the exponents. And then here, I'm going to get a positive, because a negative 1 times a negative e to the x will be a positive e to the x. And then a negative times a negative becomes a positive there, and that's e to the 2x there. So then those two drop out. All right, and so your final answer, if you simplify it, would be this guy. And then if you really wanted here, you could distribute that out. It's the difference of 2 squares. So 1 minus e to the 2x like that. All right, so just know that if it's a free response question, this is probably pretty good. All right, but if it's a multiple choice question, you might have to go all the way to this in order to find, all right, the exact match on your test or the AP exam. All right. Okay, so now let's move on into, all right, integrating, all right, e to the x, all right, which is a very simple rule as well. So the integral of e to the u du is just e to the u plus c. Now remember, if we're doing an indefinite integral, remember that plus c, got to have the plus the constant on there. Now with this, the good news about these type of problems is that anytime you see an e to the x in an integral, it's really going to be one of two things. Either, all right, either the u will be the exponent, all right, of the e to the x part, or if you have 2 e to the x pieces in the problem, one of them is going to be part of the u, because we know when we take the derivative of an e to the x, we're going to get another e to the x, and you'll see that in an example in just a moment. All right, so when we look at the first problem here, all right, okay, so we can do this by u substitution. All right, so I see e to the 3x plus 1, so I want e to the u. All right, so I'm going to let u be 3x plus 1, which means that du is 3 dx. Now we don't have 3 dx, we only have dx, so I need to divide by 3, so du over 3 is equal to dx. All right, so now if I go back and substitute my pieces, I can take the 1/3 out front. All right, I now have e to the u and then du. All right, and then the integral of e to the u is e to the u plus c. Now, when we're doing an indefinite integral, and some of you got caught on this on your last test, is that when we do an indefinite integral, we always want to go back to the terms of our original variable, which is x. So I do want to go back here and substitute for u and put in the 3x plus 1, and then I have the plus c right here. Okay, so let's look at the next one here. Okay, so once again, all right, what I'd like you to do right now is go ahead and pause the video, all right, and integrate this guy, and then turn it back on, and you can hear me work through the problem. Okay, so let's take a look at what you have here. All right, so hopefully when you did this problem, you let your u be negative x squared, and then you got a du of negative 2x dx. Now, once again, that doesn't quite match what we have here. We want a 5x dx. So what I want to do is multiply, all right, by a number to do that. All right, and so the number I'd want to multiply by would be negative 5/2, and that would give me the 5x dx to give me the exact match up here. Now, you may have decided to pull that out front, and so you would still end up with a negative 5/2 out front, but you would have to divide by -2, and it all works out the same way. So now if I go back and put all my pieces in, I have negative 5/2 times the integral of e to the u du. And then once again, the integral of e to the u is just e to the u, and then we have our plus c because we have an indefinite integral. And then once again, with an indefinite integral, we always want to go back to the original variable of integration, which was x. So my u was negative x squared, and then plus c. All right, so you can kind of see how this problem works. All right, so once again, here's another example for you to do on your own. All right, so what I'd like you to do once again is just pause the video, take a look at this, work it out, and let's see how you do. Okay, so really when you do a problem like this, all right, you really have two choices for your u. It's really going to either probably be x squared or 1 over x. All right, so you typically want to start with this guy, all right, because if I do my u as 2x, or excuse me, x squared, I get the du as 2x, and I don't see that anywhere else in the problem. All right, versus if we go to this problem and let u be 1 over x, then du would be negative 1 over x squared dx, which is an almost match. So notice we have positive 1 over x squared dx, so I just multiply by -1. All right, and I get the dx over x squared, which is a really good fit here. So now I can pull that negative out front. I have e to the u du, integrate that, which is just e to the u, and then plus c. And then once again, we want to go back and substitute our original u here, and then that is our integration piece. All right, so now those have all been definite integrals. So let's talk about, all right, if we have, all right, and excuse me, those have all been indefinite integrals. So let's talk about a definite integral. All right, so now we don't do the mechanics any differently. All right, so we're still going to follow all of our basic rules. Now, here's what I mentioned earlier. Notice we have two e to the x's in the problem. And if that happens, one of them has to be your u, because when we take the derivative, we're going to get another e to the x. Now, if I have a choice between numerator and denominator, I always want to start with the denominator first, all right, and make that decision to see if that's a better fit. So in this case, I'm going to see, okay, well, what if I let u be 1 plus e to the x? Then the derivative of this, all right, is going to be e to the x dx, which is an exact match here. So then my integrand becomes 1 over u and then du. All right, and we have a rule for this, so that was a really good fit. Now, once again, if I've turned this into variable of u, so if my integrand is in terms of u, I have to have my limits of integration be in terms of u as well. So what I want to do here is apply, all right, my x values to this expression and find out what the corresponding u values would be. So if I plug in 0 for x, I would get e to 0, which is 1, so 1 plus 1 is 2, so that would be my lower limit of integration. For my next piece, I'm going to plug in 1. So notice here, e to the 1 is just e, so your upper limit of integration is just going to be 1 plus e. It's best to leave it like that. Don't try to get a decimal answer, all right, because you want it to be as exact as possible, so we want to avoid any rounding errors. Now, what we talked about in our last lesson, all right, is that the integral of 1 over u to u is going to be the natural log of u. Now, reminder, remember, when we do this, we put the u, or the argument, in absolute values, all right, because we have a restricted domain for a natural log function. All right, so when we're looking at this function, the only restriction is 0, all right, versus when we look at this function, now we can only put in, all right, values greater than 0. So we want to make sure that that occurs by putting in our absolute values. Now, so when you evaluate, once again, once we've put everything in terms of u, we don't have to go back in terms of x with a definite integral. So I would get the natural log of 1 plus e minus the natural log of 2. All right, and that would be your answer. And that's a perfectly good answer. It is the exact answer, and you can leave it in that form. All right. Now, if you wanted to, you could use your properties, all right, and combine this and do the natural log and then put these together. So if we're subtracting those, you could do 1 plus e divided by 2. All right, so that's the only thing that you could do, all right, to simplify, and that's a great answer and a very legitimate non-calculator question that you could see or something similar on the AP exam. All right, so let's take a look at this problem. So once again, what I'd like you to do is go ahead and pause the video, attempt this on your own, and see how you do. Okay, let's work through this and see how your work compares to my work. Now, once again, we have 2 e to the x's. All right. Now, once again, I'm going to pick the e to the x that's really right here, which is in another function. All right. So I'm going to let u be e to the x, and then the derivative of u is going to be e to the x dx. And once again, that's an exact match with what we have up here. So now our integrand is cosine u, and then we have the du. So now this is in terms of u, so now I want my limits of integration to be in terms of u as well. So I'm going to plug -1 in here, and I'm going to get e to the negative first power for my lower limit. And then I'm going to plug 0 in, and e to 0 is 1, so 1 for my upper limit. And then I'm going to integrate this with our normal rules. All right, so the integral of cosine u is just sine u, and I'm going to evaluate that from e to the -1 to 1. So that would be sine of 1 minus sine of e to the -1. And that's once again, that's a perfectly good answer. You don't need to put that into your calculator. Leave it just like that. All right, just know too that once again, you might see it written like this if you're checking your answers. Or it might be sine of 1 over e, something to that effect. All right, so moving right on along. Okay, so once again, just wanted to look at this. It's been a while since we've done an initial condition problem. All right, so to make sure that we understand what we're doing. So when we have an initial condition problem, what that means is we're going to integrate, all right, and use, all right, some piece of information or some point on the curve to solve for our constant of integration. All right, so if we look at this, what I know, okay, is that I have, all right, my first derivative at 0 is 1/2. My original function at 0 is 1/4. So what I know is that f prime of x is going to equal to the integral, all right, of sine x plus e to the x dx. So now I want to integrate this. All right, so the integral of sine x is negative cosine x. The integral of e to the x is e to the x, and then once again we have our plus c. So now I want to plug in my information and solve for this constant of integration before we move on, all right, to try to find the original function. So f prime of x is 1/2 when x is 0, so I have minus cosine of 0 plus e to the 0 and then plus c. So this is 1/2. So this is going to be cosine of 0 is 1, so this is -1, and then e to 0 is 1, and then plus c. So that tells me that my constant of integration is in fact 1/2. All right, so my first derivative then, f prime of x, is negative cosine x plus e to the x plus 1/2. All right, so now I want to move on to my original function. So now what I know is f of x is going to equal to the integral, all right, of this function, negative cosine x plus e to the x plus 1/2 dx. And so once again, we just want to apply our rules. All right, let me go ahead and scroll down a little bit. All right, so f of x, all right, so the integral of negative cosine x is going to be negative sine x. The integral of e to the x is e to the x, and then the integral of 1/2 would be 1/2 x, and then we have our plus c. Now this time, when x is 0, our function is 1/4. So this is 1/4, and then minus sine of 0 plus e to the 0 plus 1/2 times 0 plus c. So this is 1/4. Okay, sine of 0 is 0. 1/2 times 0 is 0. E to 0 is 1, so this is going to be 1 plus c. So now I subtract 1. All right, so 1/4 minus 1 is -3/4, and so that's my c value. So what I know now, all right, is that my original function, okay, is negative sine x plus e to the x plus 1/2 x minus 3/4. All right, so with that initial condition problem, just remember, take your time, integrate, follow all the rules that we've discussed, solve for your constant of integration, all right, and then work from there. Okay, so now, all right, hopefully you should be able to do the work here. All right, so this is going to involve, this assignment is going to involve integrating and differentiating e to the x. All right, so that's from section 5.4. All right, so go to work on that and just be ready. I'll be back in class on Wednesday, all right, to answer any of the questions you have on those.